Bienvenidos y bien materializados, estoy que me trabuco la lengua esta mañana, a este nuevo seminario, a esta nueva edición de los seminarios de fronteras de la ciencia de materiales. Hoy tenemos el gusto de tener con nosotros a Rina Jung, no digo su nombre chino porque seguro que lo iba a decir mal, pero bueno, ya le gusta que le llamen Rina, se ha occidentalizado su nombre como soléis hacer habitualmente, que viene de la Universidad de Castilla-La Mancha, en concreto de Ciudad Real, del grupo de mecánica de materiales, y nos va a hablar de algo muy interesante, que es la fractura dinámica en el hormigón, algo que normalmente no se tiene en cuenta y que sin embargo es muy relevante. Ahora os voy a hablar de su currículum, pero me gustaría hacer una pequeña mención acerca de cómo la ciencia nos muestra que la colaboración internacional es importante, que probablemente la ciencia es el mayor logro de la humanidad en su conjunto y no importa dónde se genera, porque las ideas, la ciencia, se comparte libremente y no entiende de fronteras. Rina, como podéis ver aquí, en 1994 consiguió el grado de Ingeniería Aeronáutica en la Universidad de Beijing, en la Universidad de Aeronáutica y Astronáutica. Luego de 1996 a 2001 realizó el máster de doctorado en el prestigioso California Institute of Technology, el Caltech, que todos habéis visto en las series de televisión. Pues allí estuvo ella trabajando. A partir de ahí, 2002-2003, es investigadora postdoctoral en la Universidad de Castilla-La Mancha. Luego consiguió en el mismo centro una beca dentro del programa Ramón y Cajal, y desde 2007 y 2009 pues, ha sido profesor, doctor, y a partir de los 2009 hasta la actualidad pues, ejerce sus labores como profesora titular en la universidad. Obviamente ha realizado estancias por medio mundo, en Caltech, como habéis visto, en China, en la Universidad de, no sé cómo se pronuncia,
Zhejiang University,
además de otros muchos asistencias a congresos internacionales. Es autora de más de 50 publicaciones científicas, tiene 3 sexenios de investigación y ha dirigido 5 tesis doctorales, las que tiene en curso. Y su línea de trabajo de investigación pues, se centra en la mecánica de sólidos computacional, desde un punto de vista computacional, en métodos sin mallas aplicados a la fractura de materiales cuasi frágiles, como el hormigón, del cual nos va a hablar hoy, y a modelos probabilísticos de fatiga de hormigón, sin y con fibras, es decir, hormigones, si queréis, de última generación, los hormigones reforzados con fibra y que probablemente sean parte ya del presente y del futuro a muy buen seguro. Yo no os robo más tiempo, os dejo con ella. Muchísimas gracias, Rina, por venir, estar con nosotros, compartir tus saberes y tus conocimientos. Bienvenida y el tiempo es tuyo.
Muy bien, muchas gracias por la invitación. Soy Ignacio. Para no acabar hablando Spanglish, yo voy a directamente paso a inglés. Okay, so the title is Modeling the Dynamic Fracture in Concrete, an Eigensoft-Union Mesh-Free Approach. So this work is called, in collaboration with Pedro Navas, a graduate student who just defended his thesis 10 days ago, with Professor Gonzalo Ruiz, and also Bori, who's from Case Western Reserve University. Okay. Since I'm going to be talking about concrete, so I want to show that concrete is the material both ancient and modern. So here, the first picture I'm showing here, this is the Roman Pantheon built in 128 AD. So it is still the largest unreinforced concrete dome in the world. I guess most of you, if you have gone to Rome, you might have seen this dome. And this is the natural light comes out from the top part. And the second one show is the Los Angeles Cathedral. I was in Los Angeles for 5 years, but this was finished in 2002, 1 year after. The Cathedral of Our Lady of the Angels, actually. This was designed by a Spanish architect, Rafael Monet. And this is made of architectural concrete. Actually, if you go to Los Angeles once go inside, and it's marvelous work, very spacious and with very modern design of this cathedral. And the third one I took from the webpage of the company Acciona. So Acciona is building wind towers, which is called Acciona Wind, I think. So since now, in order to generate more electricity, the tower are required to be higher and higher. So in this case, the traditional steel towers actually has problem of resonance because the working frequency is rather low, while concrete in this case offers an cost-effective alternative to steel for high-rise wind towers. Okay. Especially in this case, as engineers, we are interested to know what is the dynamic behavior of concrete. So I would like to show that in Sierra in University of Castilla-La Mancha, in the group, what do we do with concrete? So this is our lab. So we can do both structure and material tests. Basically, the mechanical characterization of concrete, like the tensile strength, compressive strength, fracture energy. And this, to see, this lab was built at the end of the last century, so it is quite new. And I would emphasize that below this strong floor, we have our self-designed drop weight machine. This is the one that we use to do dynamic tests. And this drop weight machine can drop a weight from top, it's like 2.5 meters, can drop a weight up to 120 kilograms. So I'm showing here, this is a video that we are breaking one concrete beam. That's how it works. So this is our high strength concrete after their impact is being broken. So I myself in the group, I'm in charge of the numerical part. So I'm going to show here that some previous work that we used to mold fracture through cohesive elements in finite element framework. So these simulations are trying to show how the fracture propagates in a concrete beam that is being reinforced with both transversal rebars and longitudinal rebars. This series of experimental tests was published, which is the work of Carmona, Ruiz, and Del Viso, who are the both graduate students of the group. And the first row of the three pictures I'm showing is a beam that is without any notch. So what you see here, so these colors is to what extent the fracture has been extended. So you see how the fracture becomes localized at the central part of the beam without the notch. While this row corresponding to a beam that has both transversal and longitudinal rebars, again, so this is numerical trials that are carried out. Without the notches, you see when we have a longitudinal rebar, they are more spread or distributed micro cracks before finally it localized. While these two images are for this beam, they're experimentally tested beam. There's our transversal rebar here. We see how the fracture that has initiated from the notch and propagates away. So the following I'm going to see is a video to see how this fracture or this crack, you see this is the longitudinal rebar, and this is the crack that you see that it propagates along the element boundaries. and this is a transversal rebar. The red color corresponding like a crack that has been, it has become a stress-free crack. I have to say this is a nice video, but see here, it goes along the element boundaries, but here, since the predicted crack does not exactly align with the element boundaries, it becomes zigzag. Okay? And this simulation was carried out actually it was a static test, but we had to implement a quite complicated static dynamic algorithm to predict this part, which is a dynamic fracture within a static loading. And this video, by that time, it was 6-7 years ago, it costed 2 weeks to run. I have to say I didn't use any modern PC. It was a quite high performance workstation to run these calculations. Of course, this is 3D. And for the numerical part, since we need to do many parametric studies, and this is not admissible, so we try to look for some alternatives. One of the methods was, of course, mesh-free method, so that the crack is not aligned along the element boundaries. So the rest of the talk is following this outline. I'm going to first speak about the mesh-free methods and also the corresponding shape functions that we're going to use. And the eigen-erosion approach to brittle fracture, and the third one is the eigen-softening approach, which is the one that we developed to quasi-brittle fracture, which is for material like concrete. I think I will speak about the numerical simulations on the dynamic fracture of concrete, and later on some conclusions and future work. So, some basics on the mesh-free methodology. So here what I show is a cut from a finite element mesh. What you see, these red solid circles are they actually the integration points. For example, if this is a triangle element, of course in 2D, these blue circles are the nodal points, and this is the integration points. So if we use a mesh-free approach, what we do is take out the elements. But we still have these integration points and the nodal points, and how they are going to relate with each other is through our circle influence defined by a radius. Okay? The shape functions or the mesh-free method that I'm going to speak about is we're going to use the same integration points also as material points. So this facilitates that we always have the mass conservation. So there are many other flavors of mesh-free methods, but I'm going to talk about the one that we have implemented. So the one thing to speak about is the shape functions, because all the numerical discretization are based on the shape functions. So these are the two types of shape functions. One is the polynomial part type. This is a Lagrange polynomial function based on many nodal points, because if we want to reach higher order of accuracy, we want to use more nodes of interpolation. And the disadvantage of the polynomial part is that if we look at those two shaded squares, is that this part, they are negative. So we will want to interpolate some function. We do not like this negative part. This is not physical when we try to do some interpolations. While on the right side, what you see is one type of exponential functions. So those are the nodal points. You see this is our 3D plot. If you look at in 2D, the nice part is that we have this bell tower shape Well, these points, they may approach to 0, but they don't go to the negative regime. And from the many types of exponential functions, I'm going to speak about one type, which is the shape functions based on the principle of maximum entropy. So the principle of maximum entropy is the information theory, which is talking about unbiased statistical inference based on the nodal data. So according to Jaynes, this principle says the least biased probability distribution is that which maximizes entropy subjected to all known constraints. So what is the role of the probability distribution here when we talk about shape functions? So here is the PA is a probability function at a node A. Okay? So when we talk about probability distribution, it is positive. Okay? So this is one thing that one property that we like for the shape functions. Another thing is the sum is equal to 1, which is precisely the partition of unity property of the shape functions. And the third one, which is the third constraint we put, actually it ensures the function is able to interpolate a linear function exactly. So this is this function, these two, the probability of node A and the logarithmic, the sum with the negative sign is the maximum entropy, which is the entropy. If we maximize this function with respect to those three constraints, we have the least biased probability distribution. What does that mean? It means that if you want to do interpolation with for a field variable, we would like to have the information of all the nodes without any bias. But on the other hand, we also would like to have our shape functions that has the least number of nodes possible, as we would like to have the least width for the shape function. So this is the extension carried out by Arroyo and Ortiz in 2006. So they modified this original entropy function with a parameter beta. So it with a function u, which is the position x and the probability p. And then now I minimize this function. Remember, before it was maximized. Now we have this negative sign. Now we have minimize problem with respect to the same constraints. And this is the type of exponential functions that satisfy this minimization problem. And if we look at specifically this exponential function, how does it look like with respect to the control parameter gamma, which before, remember, we had this parameter beta. This beta is defined through parameter gamma divided by h squared. H is the nodal spacing. So look at if gamma equal to 0.2, we have a quite spread function. If gamma is bigger, equal to 5, and this is a function that is quite localized. We have a smaller bandwidth, smaller width of the shape function. While a number in between gamma 1.8 is a function like this. Normally in the calculation we use gamma between 1 and 2. So this is something wrong with the PowerPoint. So what I wanted to show here basically is the shape function, which is an exponential function that has a sum at the denominator. Okay, this is the same function before, but the lambda parameter that doesn't show up here. is the unique minimizer for the logarithmic function of theta. So this can be found in the work of Arroyo Ortiz that I cited before. What I wanted to show here is that, maybe we just say this, once we have the proper shape functions and the mesh-free spatial discretization for a domain like this, it is for integration time tk, this is for integration time tk plus 1, and this is a deformation mapping from tk to tk plus 1. The white empty circles corresponding to the nodal points which carry the field information like displacements, velocities, and accelerations, while the red solid circles are the material points, or the previously that I said the integration points. They carry, for example, the state variables, like they carry not only mass but also stress, strain, also the internal variables. Okay. So once we have that, and we would like to solve the problem of fracture. So we start with our approach that was developed by Pandolfi and Ortiz in 2012, which is called the eigen-erosion approach to brittle fracture. So the idea is that we have our 3D domain omega. This is the traction boundary conditions. This is the crack set. Okay, and the zoom of this crack tip is that if we have the crack front represented by L, and during the time step delta t, so or at time t plus delta t, the crack set has increased this amount. Okay, the energy functional that is in use is actually this. This is a strain energy function. Okay, this will be a minus sign here, and this is attraction, and this is the displacement. The external work. Okay, and the idea behind is that this strain energy functional that is being added with an eigendeformation. The eigendeformation is a mode of deformation that does not cause local energy. So it is defined as, so the delta here is the jump between the two crack surfaces, while delta n is the unit normal here. This delta c is the crack set. So the idea is that the crack set and the attendant opening displacement, which is delta, they are regarded as independent variables. So in this case, they are both accounted for this eigendeformation field. Since this would not cause local elastic energy, and this allows, when we solve the minimization problem, that we have a stress-free crack. And numerically, when Z, this is the work of Smith, Retanelli, and Ortiz in 2009, they use a regularized energy dissipation functional, which is defined as F. This is the previous energy functional. Now it is added only with two terms. This gamma here should be a small parameter epsilon, and this is energy release rate. Okay. And this is the crack set, the volume of the crack set in this delta time step delta t. Okay. And when we do the calculations, so the energy release rate is calculated to the material point P. Here, what you see here, M is the mass of the material point Q, while this is the F is the deformation gradient. This W is the strain energy before. So this MP K plus 1 is the current T K plus 1, the current time step, and it is the sum of a radius, which is of of radius epsilon, the small number epsilon. This is the sum. This is the total mass. Okay. Basically, this is averaging the strain energy function. This is a small number, which is the gamma show here should be epsilon, which is a small parameter with unit of length. And this C is a normalization constant so that we have the correct unit. And the criteria for fracture is that if this energy release rate is greater than the specific fracture energy of the material, then there's a crack formulated. And the crack that formulates, since there's a material point, the material point fails by the so-called erosion technique, so the material lost its entire stiffness. That's why the method was called eigenerosion. And this eigenerosion approach was designed for perfectly brittle materials, even though later on they have used, for example, this is for metal, which is aluminum, to simulate the mixed tension torsion fracture that was carried out by Schuris and Siak in 1987. So the work of Pandolfi and Ortiz, they choose only the central part as the notch and do a triangulation of this part, and then take off the mesh. This is what left with the initial material points. And this the field material points. See, of course, this is a quite heavy calculation, and this is the reconstructed failure surface. So you see, this is a project. This is the projected profile. There are some empty areas. This is mixed tension torsion approach. So since we want to apply this this approach to concrete, and we know that concrete is a quasi-brittle material, we do not expect that the method or the eigenerosion approach was going to work, at least work perfectly. So we developed, with respect to the equation that I have shown before, this is the energy release rate. We work on this equation. We try to get the incremental strain energy, because later we want to use a stress criteria instead of the energetic criteria. So this multiplication of the terms gives us a principal. This is a principal stress for a material point Q, and this is an equivalent strain for this material point. And this equivalent critical stress, which is our principal stress, is defined as an average of a certain radius for all the material points Q added together, and this is the sum. Okay, this definition allows us to define the conjugate relationship so that we have a stress and a strain. Okay, this is the principal stress, and this is our equivalent strain. So this is since we have this stress defined, and we are going to fill the material point P if it reaches or it is greater than the tensile strength of the material. So our idea was to be able to implement the cohesive fracture. What you see here is that because in concrete, I'm not sure if everyone knows that when the cracks start to form, it opens gradually. So it does not go to zero right away. It gradually softens until our critical opening. Okay? while the area, this is case for linear softening behavior, and the shaded area is the fracture energy. So we define a damage variable, for example, corresponding to a opening Wn. This is corresponding a softened stress, which is Fn. We define a damage variable so that when we calculate the internal stress, this variable, this damage variable makes the material less stiff. So when this T is equal to 0, we have our perfect material. Then this is the same as before. If it comes to this point, it will be 1, and then the material lost all its resistance. Okay? And if we have a specific linear softening behavior, the damage variable can be calculated directly as this opening Wn divided by the critical opening Wc. Okay? Since we're using a material points which represents a volume, we don't really have an opening. So we do our treatment, which is we define our effective fracture strength. Actually, this was a term used by Bassan. So this is our opening Wn divided by a length, which is called critical bandwidth. This is in concrete is like 2 to 4 times the maximum aggregate size. And then we have the damage variable defined as the fracture strength times this bandwidth divided by their critical opening. So if we use a general type of our softening behavior, we need to define the damage variable as a function, of course, the fracture strength and the bandwidth, and also the tensile strength, critical opening, and also fracture energy. Okay. So once we have established the mesh-free framework for fracture, remember we also defined the Arginin softening approach to fracture. We would like to model some dynamic fracture in high-strength concrete. Actually, this was one of the broken pieces of a beam. So what we see here, this is a beam that the span is 300 millimeters and the total length is 420 millimeters. It has a notch to half of its height. The height is 100, and also the width is 100 millimeters. And parallel to the center section, there was 4 strain gauges glued there. You have to measure what is the strain history. Okay. So additionally measured at these 2 supports are the reaction load. Okay, what I show here, this is the loading line displacement, which is around here, and this is the reaction load that is measured from the 2 supports. What we see here is that these were actually the first 3 curves for the loading velocity. That is 10 to the minus 4, 10 to minus 1, and this is like 17. These are for the these were carried out for hydraulic machine, while these 3 were carried out by the drop weight test machine. See, what we see here is that the reaction load increased significantly in the dynamic case. Okay, and if we integrate the area below the reaction and also the displacement, we have here this is called fracture energy. I will say it's kind of energy. Okay, because it's load and displacement, and we see that in high velocities it increases significantly. Okay, and since we want to model those tests, and here remember the drop weight, it was like 120 kilograms, and we would like to model both the projectile, also projectile and the target, which is the beam. So we need our contact algorithm. This is, I just saw a video that how we verified they developed the contact algorithm for the case, which is a benchmark test for compression of the Taylor bar. This is a copper, the material is copper. This is a diameter 6.4 millimeter. This is the length 32.4. Okay, it goes down with towards the rigid flow with a velocity of 227 meter per second. So we model that. We see how this Taylor bar is being compressed, especially here it's great deformation. The color code is for plastic deformation. Okay? And so we model the tests, use both the eigen erosion and also the eigen softening what we developed, and we would like to see how do they compare with the experimental data. This is one of the cases because in the experimental test there were 3 velocities carried out. So we compare one of the case. This is a strain gauge. This is a micro strain with respect to time, and the black dots here is the experimental data. Okay, the red one is from what we developed for eigen softening approach, while this one is for the eigen erosion approach to fracture. So what we see here is that I have to say that the strain gauge measurement, since concrete is not that homogeneous, we might not trust completely the numbers. Actually, we use the strain gauges only try to see where's the peak. But in any case, one thing is that maybe if this is 2 times or 1/2, it does not measure that much. But this case, it gives almost 10 times more of the strain. So that means that locally, the stress was being overestimated because the energetic criteria that was used for the eigen erosion approach. And if we look at the global aspects, this is for another velocity. So this is the forces. We measure both the impact force and also the reaction forces. Again, the black dots are the experimental ones. And the red ones are eigen softening approach. This one is the eigen erosion approach. But surprisingly, we look at that those 2 approaches, when they used to estimate or to predict the reaction forces, the impact forces, they give almost the same results. Okay, globally, they gave the same results. And if we look at a video how the stress evolution for the stress SY1 is the horizontal direction. Let's see if it works. So on the left side, you have the eigen erosion approach. On the right side is the eigen softening approach. What you see here is that, so we use the maximum is until 10 megapascals, the minimum is minus 10 megapascals. But I'm going to show more that for the case, if we use eigen erosion, we always have a bigger area of stress concentration. Actually, the maximum would reach around 50 to 60 megapascals. I forgot to say that the tensile strength of the material is 5 megapascals. So we also see there's a small branch if we use our eigen softening approach. So I'm going to say 3 snapshots. If we look at for 3 different velocities, this is the minimum one, which is 881 millimeter per second. For the loading time, 100 microseconds, 360, and 500. What you see here, that in all 3 cases, you have a big stress concentration. Okay. The following velocity, we see something similar, but here we already see for this we have some small branches, and this is the one corresponding to the video. we have 2 branches here. See? And since this is a mode 1 crack, actually the crack patterns, somehow we know that it's going to predict a straight crack. And we would like to see that for the 3 different velocities, what are the damage pattern. So what you see here is, because this is 1 when the material does not resist anything, and 0 it's still perfect. So we see here, when the velocity increases, you have a bigger area of damage. Okay? And additionally, you have 2 cracks. Actually, this is something that is being expected from the previous calculation. We also observed branches like this. And quantitatively, if we like to see how the area of the damage, this is the area of damage for those 3 velocities. And if we multiply the corresponding material point, the area, and also damage value, and this is the corresponding values, if this term, we sum it up and divide by the total area, this is the average damage for each velocity. We see that those numbers, they are not really significantly different. As the impact velocity increases, more materials get damaged, but not the same material get more severely damaged. So if we want to look at the dynamic increase factor in strength, so before we have seen that if we use eigen erosion, those are the stress are being overestimated, while the eigen softening that we develop gives a more reasonable number. Because remember, 5 is the tensile strength, the static tensile strength. So the dynamic increase factor for those is between 1.1 to 2.2. So we can also look at the energy evolution for the beam. Here what you see, this is the kinetic energy, the blue. The one is the dissipated, I will say dissipated energy corresponding to the fracture energy, the red one. And another one, the green one corresponding to the strain energy, and this color, light blue, corresponding to the energy input at the support. I have to say that the work that's been done by the support, we also use the contact algorithm to model the support. They are quite significant compared to their dissipated energy. Actually, if we see the following velocity, and they come because almost the same order. Okay? And this is the following one, the maximum velocity. So this is the dissipated energy. This one is the support energy, actually is higher. So it is also very important to take into account the work that's been done in the support. In any case, what we see, the kinetic energy is the significant part. Okay? And if we plot, because these 3 corresponding to the eigen erosion, this correspond to eigen softening, again, that the static value is corresponding like 0.7 joules. So the dynamic increase factor is between 1 to 2 for these 3 velocities, sorry. And one thing I would like to emphasize that we also do parametric studies for 400 millimeter per second, the velocity, and for Southern, we see that the percentage of the dissipated fracture energy as part of the total energy when the velocity is great is only 3%. That's the significant part is the kinetic energy. So just to conclude, I also to say that we have also did some trials for the dynamic fracture in mixed mode. So these 2 loading velocities, actually this is the original video that I have seen before, that you see that there are two pieces. The central part is broken, and also this part is broken. This is what we predicted for the two main cracks. Another one, if we try to add fibers, because these are the very preliminary work, we see that due to the existence of the fibers, we don't have this main crack at the loading section, but only this crack. They change direction due to the load velocity and also the account of fibers. So now I come to the conclusions. So we have established a mesh-free framework to model dynamic fracture of concrete. And both approach that the eigenerosion and eigenshifting captures the global effect like the forces, reaction forces, also the crack pattern as well. But the eigenerosion approach overestimates the stress and strength around the crack tip. And from the numerical simulations on dynamic fracture in mode 1, we see that the fracture energy expenditure is only a very small amount of the total energy in the beam. And also, as a feature work, we are applying this method to dynamic fracture in mixed mode, and we want to include explicit representation of fibers in the numerical code. Thank you very much.
Thank you very much, Rina, for this nice talk. And if you don't mind, we can change to Spanish in order to push our students to make questions. Well, es el momento de las preguntas. Muchísimas gracias por esta charla tan interesante y que nos abre nuevos campos a diferentes aplicaciones del hormigón. Y bueno, es tiempo para las preguntas. Os animo a participar como siempre. No hay nadie que tenga una pregunta. Es decir, ¿para qué vais a aplicar todo esto, por ejemplo? ¿O con qué idea estáis haciendo ensayos a tantas velocidades? ¿Qué aplicación práctica podría tener en la ingeniería?
¿Qué aplicación? Lo que queremos saber es, claro, cómo comporta el material en carga dinámico. Por ejemplo, por el caso, bueno, quizá lo de las torres no es un ejemplo, pero eso ahí sí hay fractura dinámica y se tiene que saber a cuál velocidad que se va a propagar, cuál es la resistencia en la carga dinámica.
Una explosión, un choque.
Explosión, yo creo que con este no llegamos, quizá David sí está en la parte de explosión.
Pero, por ejemplo, un choque de un camión o alguna de estas cosas. Es decir, estas cosas que parecen tan alejadas de la realidad, luego tienen aplicaciones, porque muchas veces pensamos que solamente en cargas estáticas en el hormigón, y hay muchos casos, por ejemplo un terremoto o así, donde las cargas dinámicas podrían ser interesantes. Bueno, pues si no os animáis con más preguntas, agradecer de nuevo a Rina que nos haya acompañado hoy. Muchísimas gracias por estar aquí. Esta es tu casa, así que puedes volver cuando quieras y
muchas gracias.
Hasta pronto.